All right, so now that we know about the vocabulary associated with equilibrium and how we look at those reactions and how we can talk about in terms of the concentrations at equilibrium, before equilibrium, using ice tables, etc. Now let's pull back in what we did in lab last week. Delta G equals delta G naught plus RT log Q. This is how equilibrium is related to Gibbs free energy and spontaneity. Just in terms of the terminology, if a reaction is spontaneous, back in the delta G chapter, this happens when delta G is less than 0, when delta G is negative. That is how how we know a reaction is spontaneous. In this module, now that we're learning about reactions, equilibrium, a reaction is spontaneous if the K value, the equilibrium constant, is greater than 1. And we're going to continue building on this idea of spontaneity and how it's related to the various things that we're calculating. But as we look here in this equation, this is how we can calculate a delta G if you are under non-standard conditions. And you did this over and over and over again in lab. The tricky part was the Q because we didn't have the full picture on what that is. Now you do. But again, if the delta G was negative, we concluded that that reaction was spontaneous. If the delta G was positive, we concluded that that reaction was not spontaneous. Now we can relate it in terms of the equilibrium constant. And if you are at equilibrium, we learned back in the Gibbs free energy module, the delta G equals 0. Well, if the delta G equals 0, then 0 equals the delta G naught plus RT log Q, but at equilibrium, Q equals K. So we now have this equation. Now, delta G naught is the standard Gibbs free energy change for the process. It is not a measure of at equilibrium or anything like that. It is simply a matter of looking up the standard Gibbs free energies of formations of the product, subtracting off the reactants. That is the standard Gibbs free energy change for the reaction. It does determine whether the reaction is spontaneous under standard conditions. But that is not what's equal to 0. What's equal to 0 is the delta G, the non-standard, because we're not necessarily at room temperature or 1 molarity solutions or what have you. So at equilibrium, the delta G without the naught symbol equals 0, Q equals K. We have this equation, which of course becomes delta G naught equals minus RT log K. This is the equation which relates the equilibrium constant to the standard Gibbs free energy change for a reaction. The R, as we saw in lab, is equal to 8.314. This is in joules per Kelvin per mole. We typically are dealing with delta G's in kilojoules, so you can write this as 8.314 times 10 to the minus 3 kilojoules per Kelvin per mole. The temperature is the temperature in Kelvin. Almost always, we're dealing with the temperature at 298 Kelvin. This is 25 degrees Celsius. This is standard temperature for thermodynamic studies. So what happens when we want to work a problem? So this is a problem from your practice set. This is a new type of problem. We haven't seen these types of problems before. In this type of problem, you are given numbers in scientific notation and you are asked to report the answer in scientific notation. And so this looks a little weird. Again, it's a new type of problem, but it's nothing you can't handle. So we have that the standard Gibbs free energy change for this reaction, the delta G naught, is equal to 3.0 times 10 to the 2 kilojoules. Well, that's 300 kilojoules. It's just 300 with 3 significant figures at 298 Kelvin. What is the equilibrium constant for this reaction? Delta G naught equals minus RT log K. And in this particular problem, we're asked to solve for K, the equilibrium constant. Now, this is the natural log of a K. that we're trying to solve for. We're going to see this several times this semester, so let's make sure that we can handle those natural logs. I'm going to rearrange this to solve for k before I start plugging in numbers. That tends to be easier. That way I'm not dragging a bunch of numbers around. Dragging symbols around is typically easier than dragging numbers around. So first thing I'm going to do is I'm going to put the minus sign on the other side. Then I'm going to put the R and the T on the other side. I am trying to solve for k, and it's inside a log. To get rid of the log or to undo the log, I have to take the inverse log of both sides. And I'm going to go ahead and rewrite this first, just because this is typically how we solve equations. I'm going to write the log k on the left. I'm trying to solve for k, so I'm going to take the inverse natural log of the log of k and the inverse natural log of minus delta g over RT. The inverse natural log of a log just gets you what's inside that log. So k equals the inverse log of negative delta g naught over RT. The inverse natural log is a button on your calculator. It is almost always the second function of the natural log, which is ln, which might look like in on your calculator, but it's not in, it's ln, natural logarithm. Often that second function is written as an e to the x because that's what an inverse log is. So this is actually e raised to the negative delta g over RT. K equals e raised to the negative delta g naught over RT. And you need to be able to punch this into your calculator. So you do want to make sure that you work with your calculator on these problems and that you plug them in so that you know how to use your calculator. Let me grab this and bring it up here. And now we'll solve. Delta G naught is 300 kilojoules. We'll write R in terms of kilojoules and temperature in terms of Kelvin. And we end up with K equals E to the negative 300 over 8.314 times 10 to the minus 3, 298. Be careful punching this in your calculator. Again, you want to make sure that you can punch it in and get the right answer and practice it many, many times before you sit down and take your quiz. I like punching everything in backwards. That's because I have a cheap $10 Walmart calculator, and my logarithmic function button has to be pushed after I type in what I'm taking the log of. If you have a graphing calculator, you typically hit the log button first and then punch what's being taken the log of. Anyway, you'll want to practice with your calculator. That's the bottom line. I think I remember where I was. Don't forget your minus sign. A common mistake on this problem is to forget that minus sign. Oops. And I get the K is equal to 2.587 ... times 10 to the minus 53. My instructions are to round to two significant figures. Again, that's just so that it does not take points off. The sig fig rules for natural logarithms are a little tricky. We're going to talk about them a little bit more in the next couple of modules. For now, just pay attention to what it tells you to round. So that's 2.6 times 10 to the minus 53, and I'll be typing that in and checking that answer. Just a quick note for the end of this problem to make sure it makes sense. My delta G naught was a positive 300. That indicates that this reaction is not spontaneous, and my K is less than 1, which also indicates that my reaction is not spontaneous. Those should agree. If you have trouble with this minus sign, like I said, a lot of times you forget the minus sign. That's a common mistake. You'll end up with the wrong agreement on whether or not the reaction is spontaneous. So that's a good quick check just to make sure you haven't made any math errors. So there's how we calculate that. Let's do one more. You'll see these problems on your practice set. Your numbers will be different than mine. This gives you an opportunity to practice. So in question number 19 on one of your practice sets, the equilibrium constant for this particular reaction is 4.9 times 10 to the minus 20. Notice that that means it's not spontaneous. It is asking what is the Gibbs free energy change for this reaction. Delta G naught, it's the standard, equals minus RT log K. I'm expecting a delta G naught to be positive because it's not spontaneous, so I'll double check that. And so delta G naught equals negative 8.314 times 10 to the minus 3 times 298 Kelvin. Your K is unitless. I think we talked about that earlier. Your delta G is in kilojoules. This kilojoules per Kelvin on R cancels with the Kelvin on 298. And then natural log of 4.9 10 to the minus 20. Again, as you punch that in your calculator, just make sure that you know the order you're supposed to be punching it in and make sure that you're getting the right answer. Let me punch that in. You should be punching it in as we go along. Again, a common mistake is to forget that minus sign, but there is a good quick check at the end. I get 110.158 ... You guys can double check me. That is kilojoules because of the unit on R. And it's asking me to report this to one decimal place, so 110.2, and I'll add my units of kilojoules. That's what I'll enter to double check, and you guys can double check me. Since K was greater than 1, that means it's not spontaneous. So I'm expecting a delta G to be positive, not spontaneous.